So, welcome. It's been a long day, and we are hurtling towards the end of this lovely band camp. And what I'm going to be talking about is, it's a year old, so I don't know if it's fledgling anymore, but our Bayesian Mass Explorer project. And I'm going to give an introduction to the ideas of the project, how it's built, where we're going with it, and Witek also will have some nice insights for the future. And then I'll give you a quick little overview, and then some exercises for us to close things out with. So, the principal goal of the Bayesian Mass Explorer is to have an accessible science gateway for nuclear properties. As you might guess, masses was a leading motivator for us, but we also have related quantities, so things that can be derived from variations of these masses, but also we've started to add more stuff to the framework just because it's really extensible and it gives us a nice place to proof various tools that we're developing within the band collaboration. So this includes things, like masses for experimental quantities and again these derived quantities. But we also want this to primarily be a place where you can look at comparisons between experimental values and theoretical model predictions across a wide range of theoretical models. And in the future, this will also include Bayesian model mixed predictions as well, probably in a similar framework that was presented in the previous talk. Another thing, though, it's not just dumping data on you. We want it to be a nice accessible place where you can plot both the various quantities and comparisons on the same plot, so you can try to discern trends, you can try to see if there are features in the data, and you can try to see if certain models, for instance, are predicting wildly different things to give you a sense of maybe where you should go and measure. Another goal is to give a nice intuitive interface for doing some simple calculations in a cloud environment. So we've been very lucky today that all of the examples have been able to run in Google Colab, and it's a very nice platform for stepping through these examples. But this is another modality, if you will. Another way to interact with these tools is in a web framework. So just as an example, Pablo showed this dream of you go, maybe you change some data around, and you do a Bayesian calibration instantaneously. Well, if we have fast enough emulators, sure, why not have this in a web-based environment? If you want to play around with things, you don't want to install a single package to your computer, go for it. So, just to give an example, some of the things that are on the site right now include this Gaussian process extrapolator for and in this case for 2-neutron separation energy. We have a neural network that can predict potential energy surfaces. In this case, we have the data that was in the training set, so we can see how well it does. And down the road, we also will tie this in with some of our other research software for looking at exit points and fission fragment yield distributions, this sort of thing. And we are also including reduced basis method emulators in this cloud-based environment where you can get the I should have trimmed this, but to a certain level of precision. Very quickly, you can get the predicted value of your, in this case, some density functional theory when you change the parameters. It's not a lookup table. It's actually running the simulation in this web interface. And this is something we'll play with a little bit later. So the reason why this is a cloud-enabled web application, this gives us a lot more flexibility than the traditional server-based approach. So we have the capability of running it on pretty much any backend. So obviously the software it's running Python. You don't interface with Python, obviously, but somewhere on some computer it's running Python. But this can be deployed pretty much anywhere, and it's also easily scalable. So if after everybody slams the website today, and we see that, well, when 30 people access it all at once, it gets very slow or it crashes or something like this, it's very easy for me to go into the dashboard and say, we need X amount more RAM and this many more CPUs or instances. And it's also very, very simple to scale up to new instances as well, and then dynamically load balance and such. And this is what enables the remote computation. So nothing's running in your browser, so it's energy efficient. We're not going to kill your battery. But the scalability also could allow you, if you have a larger calculation you want to do, like some model mixing in the cloud, then you can spin up a new computer somewhere in a data center, do the model mixing step that would be expensive if you had a server running all the time, but it only takes a few seconds to do it. So you have this elastic compute capability, which means that you can more effectively budget your computation stuff. So the specific resources that the BMEX project uses for the website, when you go to bmex.dev, you get this landing page. This is all just a static website with hosted on this cloud provider here, Vercel. And the styling looks pretty nice, got a beautiful logo. And it's very, very quick to change things, and in the future this will be the host, also where we host the documentation and host tutorials here. And this is all built very, very quickly. It's very cheap to operate, and it's a great way to basically manage the brand presence of the web tool, essentially, so people can go and easily access it. For the web application itself, the thing that's doing all the thinking in the back end, right now we're hosting on the Oracle Cloud infrastructure, and I can recommend them if you want to build a web application for your own purposes, just because they are very generous with their free resources, and you can get a pretty nice machine for nothing. So if you're in the proofing stages where you're not sure what you're going to need down the road, start off here, and then once you see the 30 people break it, you can scale up. And the nice thing, though, about writing these things in a very general purpose way is that I'm not beholden to Oracle. If they do something like remove my free accounts because I'm too popular or something like this, it's no problem. I can easily deploy in pretty much any cloud provider, be it on Amazon's services, Microsoft, whatever. So the added benefit of this, the cloud-based approach, I would say, that I didn't mention too much, is the budgeting aspect. So it might not be something that you care about too much, but at some point you might. Whenever you want to imagine hosting a service like this for the whole community to use, it could be quite a large upfront capital expenditure to buy a server that's really powerful to host and deliver this website to people. But whenever you go cloud, you can, again, decide what the scale is going to be, and then have sort of fixed monthly cost instead, which is easier to fit in for like a 3-year grant, for instance. Now, there are challenges that if you ever decide you want to go cloud for your particular user-focused tool, there is a trade-off between speed versus cost. If you're doing large-scale calculations that are intended for high-performance computing venues, you're not going to want to do this on Amazon Web Services. You will very quickly run out of money, and everybody will be upset with you. There's also some latency associated with scaling. Typically, best practices would be actually to have some headroom and hope that not everybody hits your service at once. So if you see you're getting into a period of higher demand, you can then scale up and be ready whenever the rush comes. For a tool like BMEX, which is targeting, I would say, a niche audience, scaling hasn't really been too much of a problem. But if you ever build something that is going to be a workhorse for a lot of people accessing, this might be something that enters into your consideration. And then finally, managing user state. So what user state means is basically when you go to a website, and you start doing stuff, and you want that stuff to be remembered the next time you go there, that information has to be stored somewhere, be it in your browser or on the server. You can decide the best way to do that for yourself when you're building out your system, but I would definitely recommend, just for data privacy reasons, to try to not host anything on your server and host it all in the user browser. This has other challenges. Users could get angry because they lost their widgets they had set up or whatever, but that's just one complaint instead of having to deal with the fines from the European Union. So right now we have a pretty robust feature set on the Bayesian Mass Explorer web application, and we are continually adding new features to it. I will highlight someone who's doing the bulk of the work because he's doing excellent stuff. But in the near term, some of the things that we want to build out in addition to our plotting functionality and our immediate applications of the BMEX software include things, include actively engaging with the community and soliciting what they want, both in terms of new features and functionality, but also how we can improve the user experience for the things that are our core competencies. So if the product that we do best at BMEX is giving theoretical model predictions for nuclear masses, for people writing proposals, or maybe fission yield predictions or something like this, we want to know if there's a way that we can make it a little easier and a little more robust. So with that in mind, you'll see on the website when you go there, but there's a big button that's a GitHub logo. If you click that, it'll take you to an issues page. And we certainly want all bug reports, because sometimes there are bugs lurking where you never expect them. But also, if you just have general feedback, we also accept this. So the roadmap for things that we have in the works right now, one includes having more robust dimensionality reduction modules. So we have this reduced basis method emulator, but right now it's just popping out the predictions for the binding interest charge radii. In principle, we have access to full density profiles, all the observables that come in your DFT model. We also want to scale this up and have different types of DFT models and improve our interactivity with exploring these models and plotting things and such. We want to really pursue deployable posterior sampling. Right now, I would say it is a bit of a pain to go to Pablo and say, hey, give me those 5 million samples from the Rose calibration. And we have some nice perspectives on where we can go to make this a lot more efficient, a lot more user-friendly, and also not have a 5 million line text file on our server. And then finally, something I alluded to earlier is to introduce a continuous calibration framework in the web interface. So this would be the user-initiated side of things, where while Pablo was presenting about, you click calibrate, or you change stuff around, and you see the posterior updating in real time. That's certainly part of it, but we're also trying to build out a scalable cloud infrastructure for automatic calibration of nuclear models, and also whenever you have new data that's introduced to a database, say INDEF or INSDEF, it can automatically hit the calibration runner, scales up a bunch of containers that do the calibration, and then boom, you have a tagged, traceable Bayesian posterior distribution for your model parameters within a day, hopefully. So you wake up and it's waiting for you. So we do have some more planned functionality, and that's going to be VTech's talk. But first I want to show this very happy photo of Landon here. He's an undergraduate student that's working with us, and he's really been driving a lot of the development for BMEX in terms of user functionality over the last year, really. So he deserves to be highlighted here. So thank you, Landon. Right now, he's working hard right now as we speak.
He looks like every day.
No. Well, he's always smiling. He's always smiling.
Smile is different.
Yes. So before we get into the session where I show you how to use the tool and give you a couple challenges, Witek is going to come up and going to present some perspectives on our further developments.
So this is going to be very short, and I am not going to give you any homework. Okay. So as Kyle said, BMEX will store results of calculations and also experimental data, so one will be able to play with various models and compare them to experiment, etc. Right? So the idea is to store on BMEX basically nuclear masses, because other quantities such as separation energies, other Q values can be computed from mass differences. Okay. But immediately you see that in order to assess the uncertainties on differences of masses, for instance, one needs to store more than just mean values. One needs to store the correlations or covariances. So the idea is that BMEX will store the covariances which were obtained in the process of calibration. Okay, so
You need
this
to
is
push on the keypad the arrow keys. Is that button?
really
Yes.
okay. So this is basically very elementary stuff. I just want to make a particular point that correlations are in fact very important when one deals with uncertainties. Okay, so correlation is usually calculated as a covariance between two quantities xy and divided by sigmas variances, right? This is textbook. And sometimes we have quantities which are very correlated, like for instance in this case there's a quantity which is called neutron skin. X is neutron skin, Y is called dipole polarizability. It is absolutely not important what those quantities are, but there are different quantities representing different physics, okay? And you see it's actually well correlated. So within this particular model, which is listed here, we can say that they carry similar information content. But there of course are many quantities like effective mass and neutron skin which are poorly correlated. The correlation coefficient R is 0.98 here, is 0.11. Statistically within this model, correlation is strong in first case, is weak in the other case. Okay? Now, so of course, this kind of calculations can help us understanding the structure of our models and tell us a lot about predictability of a model. But so consider a difference of two observables, x and y. So z is a difference, is an observable, right? Which is a difference of two observables, x and y. And we know what is sigma square of z, what is the variance of z, is obtained as through the variance of x, y, and there's this correlation, or covariance, right? Correlation coefficient R. Now, if two quantities are extremely well correlated, okay, then this correlation coefficient is close to 1. For some reason, some symbols are missing here. Okay, so if this is 1, you can see that in this case the sigma of z is just the difference between sigma of x and sigma of y. So, so it might be that the error, predicted error on the difference, will be significantly smaller, right, than those individual values. If those quantities are of similar size, you might get very small error on difference, okay, if the correlation is large. But if correlation is close to 0, the error is large, okay? So now depending on the situation, okay, the error on difference might vary. So the question which I wanted to ask are variances of differences of smoothly varying observable mode. So imagine you have observable which is very small, very smoothly changing with some parameter. Let it be proton number or neutron number. After all, this meeting pertains also to nuclear physics. So small gradual changes of some variable. For instance, mass. So consider a nuclear mass which you plot like what Kyle did a moment ago as a function of neutron number or proton number. If the mass is changing very smoothly, so the question is, what about errors on the mass differences, which we're after? We are interested in mass differences, right? Okay. Well, in order to assess this, one needs to know this correlation coefficient R. Okay, I'm just going to show you some results. So there's a paper from 2022 in which we are trying to look at two quantities. Okay, the first quantity is quadrupole deformation, which has something to do with nuclear shapes. Quadrupole deformations describe nuclear shapes. Okay, and charge radii, and those define nuclear sizes. So sizes of the nuclear sizes change for those three isotopes fairly smoothly as a function of neutron number, okay, and the same with radii. So you naively think that since those quantities change smoothly in experiment and theory, right, the differences of those quantities will change also smoothly. And usually this is almost obvious, right? If the quantity changes very smoothly, changes are adiabatic, gradual, then there must be less correlations between those individual datums, right? Is it the case? You never know until you do calculations. Until you calculate, you do not know. There's no... So this is, see, this is PC.
It's right below.
Right below, yeah.
This is a PC which basically reformatted the text box of PowerPoint. Well, we should have checked, Kyle. Yeah. Okay, this is what you get when you do this exercise. So this diagram shows how correlated is quadrupole deformation actually of this nucleus with all other nuclei, okay? So we see the strong correlation of this quantity with the neighbors, okay? And this correlation gets worse and worse as you change neutron number and proton number. Sometimes the effect is dramatic. Look at this fellow there, okay? So this star is very well correlated with itself, of course, 100% correlation. But you just go to the neighboring nuclei and correlation is lost. And you saw on the previous diagrams that trends were smooth. Many theorists doing very expensive calculations, they do not have stamina to calculate uncertainties. And they will say, well, things change smoothly, correlations are large, and then errors are small. Okay? Not the case, not always the case. As you can see clearly, until you calculate, you do not know. Now, so we are now currently trying to write BMEX, because we are now currently trying to implement this correlation feature into BMEX. So we'll be posting mass tables calculated using different models with covariances, and having those covariances will allow users to calculate any mass difference with errors, and this would be of particular interest to people who are doing astrophysical simulations, such as astrophysical networks, okay? So this is the work which will be done with several people. Okay, the second thing I wanted to mention is about Bayesian model mixing. So you got excellent introduction to this, and also you got your hands dirty doing these exercises. I just wanted to say there are things which can be, there are various things which can be done. So this is the slide, part of the work with collaboration with Witek Nazarewicz and Leo Nevcourt. So Matt mentioned this particular choice of weights, okay? So the weights are normalized to 1, they are non-negative, okay? We can parameterize those weights very nicely using Dirichlet distribution, okay? And this is defined in this way. So basically go from the weights to hyperparameters alpha, and those parameters alpha, they have very nice interpretation. If those alphas are less than 1, then we can talk about model selection. For instance, you see those weights will basically, weights will tell you whether a model is selected out of 20 models we should consider, or we can just proper model mixing. We have more democratic situation. So this is something which we want to implement. We want to do BMM, Bayesian model mixing, with those Dirichlet weights. And the second thing is to make those weights dependent on the domain. Now those weights, as Matt showed, depend also on the domain. So the weight depends on Z and N. Locally, okay, the weights can favor a particular model. Okay, so this makes sense. So these are examples of such calculations with local weights. So the table shows you the results obtained by using different models. Okay, this is for training set, data set, for testing data set. You know, I had those shown on the previous slide, but this is not important. You see, individual models give you RMS errors of this kind. Those models are not perfect. They are very imperfect, in fact. Okay, so this is the typical accuracy which those models produce. Okay, when you do Bayesian model averaging with weights which are independent of the domain, you dramatically, significantly reduce the error. And those are different variants of evidence calculations. So just, you see, they are not very different. But when you do local weights based on Dirichlet, you can actually go to pretty impressive numbers, 0.25 MeV, okay? It's really very, very good uncertainty for a model prediction. So those will also be added to BMEX. This kind of model mixing with Dirichlet description and will be put together with covariances. Okay. Voila.
Excellent. Thank you very much.
Witek, I had a question.
Yes. Oh, I'm
So
sorry.
maybe just a comment, maybe just on the slide 2.
On the slide 2.
Yeah, that one. Yeah. So here, I mean, the R can be even negative, right? So for negative
No.
one, you have even larger variances, right? If I'm right.
R cannot be negative.
Why not?
No.
So it's basically anti-correlated, right? If you use negative.
Oh yeah. But we are talking about absolute values here. So R, yes, you are completely correct.
So
R can be -1.
so then
This is your point. Yes.
Right, so in that case,
Yes.
then the variance will be even larger.
Yes. Yes.
So if two
Yes.
cases
But then I can call my another variable minus variable.
Right, so if they are perfectly correlated, we can
Perfectly correlated and perfectly anti-correlated is really the same stuff, because instead of quantity x, I can call it quantity minus x.
But that's not what it says, right? I mean, here if you do in the perfect correlated case, sigma z is sigma x minus sigma y. In the perfect anti-correlated case, it's going to be sigma x plus sigma y, right? Because that is going to be a plus sign to sigma x sigma y in the expression. So this whole thing is a perfect square.
So sigma x, sigma y are defined always positive here, right?
Right, that's right. But I'm just curious about what happens when Rxy is -1. Then I think sigma c is going to be sigma x plus sigma y.
physically those two cases, in my opinion,
Yeah, I
absolutely
mean,
equivalent. Yeah.
It should be
Yes,
equivalent, but
yes.
I mean, this expression gives
But the expression is statistically correct. Matt, is it correct?
I don't know. I
Okay.
can't see the other upside down.
Maybe you can find out later.
Yeah.
I think you're right.
All right. So with that, then we're going to go into some playing around with BMEX itself. And we don't have that much time, so I'm going to limit the tour of the tool that I was going to give you. So I'm going to go ahead and show you the challenges, which are more just to guide you in playing with the tool. So number one, whenever you go to bmex.dev, that's bmex.dev, capital doesn't matter, but it's easy to read. You'll see something that says like challenge 1. If you click that, it'll take you to a pre-made view where you can start to go ahead and look at some interesting features. So what I recommend is talk with your buddies there and see if you can figure out if you see any patterns or trends or something. See if you can figure out what those trends might be and what you're learning from looking at this data. And then move around, see if you see other features popping up in other areas of the nuclear chart, see if that fits in with your hypothesis. And then finally, change it for protons and see if similar trends exist. 2, you could do this thing with this deformation that has to do with nuclear shapes that Witek was talking about, where you change the quantity kind of on the view that you were looking at, or plot these things that are called 1D chains, and see if, for different models, for a given set of nuclei, if there are vastly different predictions between them. And with that in mind, think, okay, well, if I could determine the shape of one of these, which one would give me the most bang for my buck to actually measure into that? And then if you're an overachiever, which you can't be with 4 minutes, you could go and actually see if you had a couple different candidates, which one do you have the most rates in a place like Effort? Which one is actually more reasonable to measure? And then finally, if you're interested in the RBM side of things and you want to do a sort of, want to build a nuclear snowman in a sense, go play with the model parameters, see what affects what, just really try to get an intuitive feel for these random letters basically that you don't actually know what they mean, and see if you can build the biggest lead or the most bound oxygen. Just play around essentially and see if you can uncover some things. And if you have any questions on anything, cloud computing or BMEX or anything, go ahead and ask, and we'll walk around for these last couple minutes and see if everything's good. Sound good? All right, go for it. And if BMEX crashes, please let me know. I can't do anything, but I am curious. Nope, yeah, we know that. We thought about putting an Easter egg somewhere around, Z equals 4 million.
Who says we haven't? We haven't. That would be challenge 4. Find the Easter egg.
You can play around with it. Is it working well? Lots of cool features. You can export publication quality PDFs straight from the website.
To use extended states of the same spin. Let's say if you want to do a mass prediction, can you use?
Yeah, sure. This is what experimentalism is.
I know. What I'm saying is, are any of these,
Yes, sir.
are the, you train on,
That was the with the
We just use
surface means. Which is basically how it efficient.
However, I don't know what, do you know
So these two are the formation parameters. One of them makes
yeah, but that doesn't get,
and the other one makes in nuclear.
different words?
Each one
figure state of carbon
these, but
no,
making one part more than the other.
this.
And eventually they the funny thing is,
Right,
you
but
put
then
the
you want to know the ground state. Before you knew that,
how hydrogen was
carbon 12 is a useful piece of information.
Yeah, there are bounds.
For instance, with a paper,
Yeah.
you know, zirconium 80 usual
Big range of energies.
binding there, which we're trying to combine the results of the Bayesian model mixing.
Okay, so there are many things
Sometimes
here. Discharge radio
Where do you get the
No. So what we do sometimes is experimental data. Experimental data for testing calculations.
That's what I'm asking. This is the training set for
and you can
silent
change many of
states
the parameters. So when you have
We can add this.
T greater than TZ.
We can add this.
mine has no challenge one is on the other beta.
This is so
This
this
is not flooding, this is actually calculating. So
because there are still much less. Errors in theoretical models.
Yeah.
But
This is a 250 kilovolts is amazing.
Yeah.
which is reflecting what is
Before you got to that, this mixing, delay mixing, you had stuff that wasn't too much better than finite range liquid drop or the other.
You can see.
But then when you did that, then you got half.
But we can still do better because we can, of course, we can correct statistically each of those models, and then we can. Okay. But then there's a danger of overfitting. You can overfit, of course, your calculations. But as you can see, we're making nice progress.
This one I'll play. Up to this point, it wasn't going to play, but this one I'll play. I haven't done anything. Yeah. Yeah.
Okay, great. So tell us your comments. If it crashes on your iPhone, we'd like to know.
Yes, really cool, right?
I don't know. So are you?
I would have covered this before.
No, this is just a very useful. What's going on? Machine learning.
Is that the odd number? Because I know that you were.
What I will mention now, but I also will mention other things. There are so many things.
Yeah, so,
I remember.
How's it going over here?
Behaving all right?
So, because it's not that
oh, if you just want to know, yeah.
which are constrained.
What's the back I did?
Right.
It's technically,
So he's not.
it takes a while to get used to it.
See, so totally equivalent to this.
Have you ever taken like a nuclear structure course before?
This is what we do. This is slightly different.
Our main focus is
Yeah, so you can still understand a lot from that, but it depends on what they went over.
finding that.
Yeah, where the surface softens.
It's not trivial.
Okay, so
Each surface.
I'll be honest, I didn't make all these. One of the things you can do is you can look at differences. So I assume what's being shown here is sort of like a central difference in the
So that's why once you go back to train these, it's telling you that then you can change
binding energy. So you take the three neighboring nuclei, and imagine a two, a 3 point.
It'll take
I'm not entirely sure it is super relevant. Certainly I don't spend my day talking about it.
What you can come
Like he's not so stable, so he's not very well.
and use this information basically for training.
Try to where
Train how you run it.
So wait a minute, so you didn't have a nectar on it,
And that's instantaneous,
It could
because once
be
you've
Picture
done it
that
for the entire
couple
chart,
also.
81 and 82.
okay.
So so
you can just, for those type of, yeah, for those type
and
of
then you
programs,
can
if it's a Gaussian process,
80 and 82.
all the dividing it.
I'm going over here. It's a website.
Are fixing and so it's not true. So we know it's not true.
Make some features.
Yeah, so that's good. You can always take more features, but I can say that because I'm not the one in charge of
Like I said,
is there anything in particular?
I mean, I
it
think
does not.
I'm gonna give you more be able to plot ratios.
There should be some difference.
Oh, yes, right.
Ratios.
Well, that's fine. So like, that's what
You don't
What is your problem?
the wording train.
No one can check that out. I've got a doctorate, and other people live
like being able to sociology, psychiatrists,
don't go into details. What is the process?
So one of the things I want to show
Yeah.
that would be really nice. Just for
It's really hard to do because everybody has their own
I mean, if you could see partial half-life, say like, if you're on
I never would have thought about it.
But then I guess the time.
apparently the people in the art process
I'm not everyone in charge of how you would handle that. One thing you could imagine
makes reverse situations.
for
I
instance,
forgot what exactly.
I think you
They
can run a lot of
find evidence for
It's only open 9 to 5.
vision.
I don't know exactly how to do it, but if I were my way, one thing that would be useful if you just want to display down, being able to download why was put on.
I know more animals.
Number two, the vision is 100.
Some types of and you know, instead of going to get, you just like press this button to download. And they're more partial
has dropped. And the alphas dropped off the net.
come up with many features.
Good.
What's happening with those two?
Add them to the issues.
Okay, so normally you'd say the vision,
And I think we can add a label to it if it's like a feature request.
well, because the facility without
Or like an enhancement. That's what I would put.
okay, that's, so I'm saying explain. Not just by the generic statement, but by using your vision model to say,
Yeah.
because this is one, the case of one end, it's the most studied vision.
If you have to close, I recommend. If you have to close, you can tell them what was those two signatures because that found it very interesting. Those were my.
Oh, okay. Well, just whenever it looks like Dick wants to start his.
Yeah,
I can translate it.
yeah. I'm just saying it because I think people will enjoy knowing. And you can make the case of how, in this case, we knew because we understand the physics. But what if we can figure out things?
Yeah, well, X is close to 1.
So it was not that
So
obvious.
small changes, small change on the barrier.
You can modify all those parameters under emulator.
Action is to expand.
So they have
However, it doesn't drop
This is
entirely
not surprising.
about that.
Okay, but
It
here,
doesn't
but
drop
the case
the
I'm putting on the
down
table
because we're at like
it's got
Yeah,
vision
so
and
you're trying to make the
it's got both, and it's they're both well known.
yeah. I think you're right.
So I'm just saying,
because I want
the territory up there,
and then as I go
they haven't
on,
changed.
So one way in which
Yeah.
First look at it, I said, oh, that's
It's not.
Well, precision because the outer barrier comes
The way that everybody needs it.
outer body does nevertheless. Some of them are like it's on the one bar. But it's small. It's very small.
What's
Well, it depends.
it's got to be, you got to be saying there are cases where the alpha.
Yeah, right now. Right now.
That's why the alpha came in.
I don't. There's probably a limit. This everything happens.
It seems like it, you know.
Yeah, I think this is what he's
The Q values and we know where Q now dominates. But I can show you. Nice two-dimensional plot.
These are north. These are north, west. Right? Absolutely north. That means
Those where those are very properly.
yes. So they're northwest. That means that a diagonal decay up there gets you much closer to stability. That means Q value, Q alpha, that's what you get rare earths that alpha decay. Neutron deficient rare earth alpha decay. For precisely the same reason.
Yeah, you mean like one
There, I was going, I'm going just a little northwest.
So that's how you get it.
Color.
you'll be like Mercury,
Don't know that stay low. See that he's blind to the stay low. It's just showing you when there's a change. I don't think
Well, if your Q values are good, you should be good.
so you're getting heavier and more stable.
Well, you got a diversity, so I
And then what's the that's probably just because so look, you know, when pre-compute things sort of have to stop at some point. Well, I mean, when you hit training, it's not really training, it's like fitting out to all the available data, and then the prediction matrix has to be repopulated at some point. I guess there's a server stability.
They put barrier penetration. Barrier penetration.
I respect that.
Because of Geiger novel reproduction.
Every server has to be.
Yes,
Okay. Next.
although Geiger not only was like 20 years before we got
Right. Yes. 11, 12.
Did you want to do
So.
The one below.
Oh, no, I was saying.
Well,
How am I doing so far?
very successful.
Things are not.
All right. Now, next Geiger. Geiger model. Okay, so we move into two protons. Yes. So what is the Geiger model? And how hard is it?
Why do you talk about why don't you talk about
I'll tell you. I'll tell you. Because one proton doesn't add anything more.
Is that a KEV or?
It adds very little. Let's wait a minute.
Yeah.
What is purity? What do you teach?
So these are the different functionals.
You said action.
Is that unobservable?
Primarily for something observable.
And it was also the same. It is samples. We have not reimagined it. Go push the. You need to know. But you don't need the.
Let's just say we're in a WKD. And it only depends on that. So, now I want to go to
All right, everyone. So we're going to transition away from BMEX land, and Dick is going to give us a great recap and coming attractions for what band is doing. Just to give you a sense, just to give you a quick answer for challenge 1, you probably saw these like white bands in that plot. That's a signature of the magic shell gaps. So you may have figured that out when you notice that it's happening at 82, 126. All of these.
If you happen to know that those were...
If you happen to know, but if you didn't, now you can. And then maybe this gives us some perspective of, by interacting with data, there may be other trends that we haven't noticed, essentially. And then you go and study those in more. So,
Has it crashed?
I don't think so. No.
Anybody have any, or even slow?
No.
Some slowness.
Some, yeah.
You know?
Certain things like the Gaussian processing and the neural network emulator, those are doing some serious calculations. So if everybody did that, then it might be a different story. But I'm glad to see that it maintained its stability. This is probably the biggest simultaneous test I think we've had of BMEX.
Flush all the toilets at the same time.
Yeah, pretty much. Thank you, guys.
Okay, so we're going to just ease into the reception with a little bit of a recap of things, point you to some things coming up this week and beyond, and talk a little bit more about experimental design in the case of thinking about designing physical experiments. Okay? So we wanted to remind you of a few things that we started the day with Lesga's presentation. This project that is behind this band is funded by the NSF's Office of Advanced Cyber Infrastructure. So they're looking to create infrastructure for the community and beyond. You know, we're looking to do good physics problems and do frontier statistics problems, but to give something that everybody in the community can contribute to and use for their physics. So, reminder of behind all this, there's a lot of nuclear science motivation. Essentially, in every case we have an important problem, we're limited by model uncertainty and dealing with it. Okay, so this is from the big projects like the properties of the nature of neutrinos, the understanding nucleosynthesis, lots of things in heavy ion collisions to understand the phase diagram of UCD matter. Many of you would be involved in reactions and determining nuclear data, and maybe everybody, whether you're a theorist or an experimentalist, should be conscious of the need to have uncertainty quantification for planning experiments. Okay? Experiments are expensive, we pay for them, other people pay for them, we have to make them as effective as possible. So one way to say the goal is to build a framework that's generally useful to do all aspects of the uncertainty quantification in nuclear physics, including the model uncertainties, and provide examples of its use. So that's what we've been telling you about. Okay. Another way to say that is we want to facilitate principled uncertainty quantification in nuclear physics. So this project started in July of 2020, and at the very end I'll show you the timeline for where we've been and where we're going. We've pointed to this website for papers, talks, and software. I'm actually going to just pause there a second. One thing that we're talking about putting more on those things, little videos to describe how to do things. Okay, so just a question, quick survey and stuff. How many of you looked at the video one of the videos that Pablo and Frederic put together? Okay, so a lot of stuff. We'd be really interested in knowing your feedback up there. I don't think I'm going to put you on the spot now on things, but let us know what you found useful, what would be more useful to have that, and we're going to accumulate some there. We have our own band YouTube channel, so I'll actually ask, anybody have any immediate comment? So let us know during the reception. Okay, so we had this big framework, and now you've seen all this stuff, so maybe we can put together the big picture here. So starting on the left here, we have our physics problems. All of you have some physics problem that you're working on, and maybe there's also experimental goals, things that you want to do. We go through building models and various components of that, like building likelihoods and priors, and we have these 4 sets of tools that are going to play together to give us our results. The overall framework of this and how it goes, you are now prepped to read this paper if you haven't seen it before. This is the one that we wrote as kind of a guide to what we're trying to do, and maybe you could just say a guide to that diagram. We call it the Band Manifesto, and you can find it there, and all the other publications that have been filling in these details as we've gone through the project. Okay. So let me just step through those things quickly. Up at the top, emulation, so just in a line, these high fidelity models are the models that we build to do our calculations. May or maybe always too expensive, so we're going to use an emulator. You learned hands-on about Gaussian process emulators through Surmise, and also this sort of area of reduced order modeling emulators. Okay. This whole day, basically, on Thursday is devoted to emulators. It's a big topic now. Essentially, it makes all of this possible for us. That we can do Bayesian analysis on things. So Pablo and Daniel will be giving more formal talks on things related to what you were all prepped to learn. I'm also giving an overview talk, but there's other people too doing things, more Gaussian process results, and you'll hear other things on eigenvector continuation. Okay. Next, the model calibration. So in the future, we want to have full Bayesian parameter estimation and uncertainty propagation. So this has been a dream for many of us. Witek and I were talking before about how there was basically none of this. I mean, even a little over a decade ago on this. Now you want to calibrate your parameters, meaning update the distributions based on data, including model uncertainties and things. So you'll see, at least in some of the talks, that this is now realized that everything is together. You wouldn't see that even a couple of years ago in most of the subfields. Dan will be talking on Tuesday a very nice work on doing Bayesian calibration for heavy ion collisions. So look forward to that. Okay. Model mixing, we talked about that a lot. We look forward in the future to other applications with the Towerette software. This is something where you can use your imagination about places that you might find model mixing useful. Certainly in heavy ion dynamics, things with the nuclear equation of state, talked about that with some of you. Things having to do with effective field theories, for example, where you have different versions of the effective field theory, either with different degrees of freedom or different implementations of those things. And this is one that I'm from this field here. It's always been kind of a challenge. You know, people have these different ways of implementing it, and not a good way of combining their results to get a better result for predictions. Okay. It's more people have used the different ones that say, oh, okay, maybe that's roughly the uncertainty. So it's not very systematic. Okay. Experimental design. So a point that I'll be making on the next slide is next few slides is about requiring uncertainty from experiments and models. Oskar gave a nice introduction of different types of experimental design, and she'll have a talk on her work on this tomorrow. There's a lot of frontier work to be done on this, and so within BAND in our last couple of years plus, we'll be exploring alternative approaches and looking at other examples of this. I want to highlight that when we get down to do this, this is really enabled by all these other pieces that go into this. Okay? And you'll see why that looks like that in the example on the next slide. But we need to emulate things. We have to calibrate our models. And when we're looking at experimental design, we want to have all the input from the different models in, not just individual snapshots of what these models. By the way, I should have said this before, this is a good opportunity if you want to interrupt and ask some question about something that's been bothering you on any of these things all day. But you're invited to do that anytime for the rest of the week. Yes, sir.
So, you mentioned 10 years ago we didn't have many of these things. How were usually experiments designed for the last 5 decades?
So there are various things done with experimental design. Maybe one of them, let me answer that with the next slides here and tell you what happened in some particular case. So let's think about some ideas of doing experimental design. Where here I mean in this case doing an actual experiment. And this is in a framework where we're going to introduce a so-called utility function, which is going to tell us how much we gain by doing a particular experiment. So we're going to say there's a particular design, and just to make that easy, imagine we have some experiment where we have control over how much energy is in the beam and where we put our detectors. So looking at that schematic that Pablo had for scattering. And that's going to be the example on the next page. So given all the different places we can put those things, we can't do them all. Okay? It's too expensive. There's not enough time to do these ones. So you have to make decisions. So this then comes back from what decisions do you make? So here, what we're going to do with this utility function is see for each design, we're going to average over potential experimental results from each design. And we're going to maximize the expected gain from this. What are the goals of these? Well, it depends on the experiment that we're doing. We may be trying to get some observable quantity more accurate. There may be different models we're trying to decide between, or in this particular case, we're going to try to determine an example I'm giving, the parameters of the theory. So this is what is often called theta in our discussion for here, for various reasons. If you look up the paper this comes from, this is a vector of A. So that's a series of parameters. So one way to think about the experimental design is to think about, this is a corner plot with some interesting shaped prior distribution is this blue, and the posterior, let's just take the black, this one here. So the idea is the prior is before we got some more data, the posterior is after. So you notice the area of this, or if it's in more dimensions, the volume or the hypervolume of this has shrunk. Okay? We know the answer better. In this case, two quantities that don't matter what they are for this case. So the idea qualitatively is, at least, is how are we going to design our experiment to shrink the posterior for the quantities we're looking for as much as possible. So one way to define this here is this slightly scary looking expression here. The D here is the design. So that would be the choice of where my design, say energy and detector position. We're going to look at that over all the designs and look to maximize that. So what are we integrating over here? Okay, so in this one, the A's are the parameters. So notice we're integrating over those, and we're integrating over all possible outcomes of our experiment. So we're integrating over a lot of things. If we really have to do that by sampling, that's a really good motivation for having emulators. What is it that we're calculating here? Well, the statisticians might recognize this as Shannon information showing here. If you're thinking of entropy as a physicist, right, we got a P log P type of thing. So we're comparing the information, again, sort of before and after. Under certain conditions of linearity here, you can actually do all of these integrals, and you basically find that this is the ratio of the log of the volume before to after. Okay, so how much it shrunk. All right. So we can do this thing. What does it look like in practice? Let's do an example. And the example here is designing future Compton scattering experiments, where we have a photon beam that's going to give electric and magnetic fields. So you can think of the experiment as putting protons or neutrons inside of magnets or capacitors and watching how they polarize. So we want to characterize those very fundamental properties of the proton and neutron, these polarizations. What do we know? Well, what are we trying to do? We want to know what beam energy and what angles are measuring this are most useful. What do we know? Well, there is some data, there's information coming in. We have error bars on these polarizabilities. We know that there's experimental constraints from the particular experiments that we're doing. And we have theory here. So this is something called chiral effective field theory, which is our model for these polarizabilities. And we know that one feature of those is that they get worse as we go high in energy. That's going to create some tension here because on the experimental side, you want to go up in energy to get more counts, to get better statistics. So what we're going to do is do a Bayesian analysis of this and see what it looks like. Okay, and this is the reference you can look for this. So here again, I just wrote down, here's the thing that we're calculating. And here's our design grid. There's 4 different quantities that we might try to extract. So let's just pick this one. Some difference in polarizabilities. On this axis is the angle where we're putting our detectors, and then this one is the beam energy. Experimental constraints are these gray boxes here. You can't, there's some limited range of angles you can go and a limited range of energies. This is a calculation that is doing this over this entire plane and coloring it according to how big this utility is. So you want it to be as dark as possible. And what is coming out of here are the 5 best measurements to make for this. So this one is saying that you should sit at a particular, if you only could do 5, sit at a particular energy and do 5 different angles. This is without any theory input. So this might be what happens if you design your experiment sitting down among, without taking into account the theory that you need to do to extract these numbers from the experiment. And you decide this is the best place to get leverage on this quantity. What happens if you put in the fact that the theory that you need, this chiral effective field theory, it gets worse as you go this way in a very predictable way. We have models for doing that. Well, you get what's at the bottom. So before you said you should measure these ones up here, this is basically said if you do that, you will not learn what you think you're going to learn. You should really measure them down here, which takes into account both the theory and the experimental. So clearly there are very different implications, and clearly this is very important if you're going to do a very expensive experiment to make sure you get the most bang for the buck out of this. So that's one important thing, and you can extrapolate this to any type of experiment that you're doing, whether it's high energy nuclear physics, low energy nuclear physics. So this is really what we hope to have a framework that facilitates doing this in a robust way.
So Dave.
Let me just ask about questions on that. Go ahead.
I can ask later.
Yeah.
So this is assuming that you have good theory.
Yes.
But you can imagine what will happen if theory is provided, poor model, then experimentalists spend long time doing your variant B, and results are not satisfactory.
Mm-hmm.
Hell will break loose.
So yeah, you actually, in this particular case, this is not a matter of the model, theoretical model reproducing the data and doing one. This is one where you actually have that theory necessary to extract those polarizabilities are the low energy
Exactly.
Yeah. Okay. An interesting thing is in this field, there's this kind of competition between people who use dispersion relations and use chiral effective field theory, so it seems like a nice opportunity to do a model mixed experimental design. Is there anything? Okay. Oh, go ahead.
This is just about the figure. So
Yep.
that shift that we introduced, that bottom point, it looks like it's a value of 0 utility.
Mm-hmm.
Why is it deciding that that's one of the points that we should include?
Yeah, that's what comes out. I'm not sure.
So maybe this is related.
Is it taking into account all the other information too?
Yeah, so part of this is about correlated information here,
Okay.
right? That the idea is having things over a range of energy. So this by itself doesn't help, but in combination with the others is presumably what it's doing.
Okay.
But I'm just supposing that. I actually.
I think I have a comment.
Yeah,
that
go ahead.
maybe see that in the previous slide that you had, your thing is a function of D, the data, where you put the data.
Yes.
And in this case has to be a function of 5-dimensional quantity. It's a 5-dimensional quantity, each one with 2 things. And here you're only programming it maybe for one. Like the entire thing depends on the locations of 5 measurements.
Yeah.
This plot cannot have all that information. So maybe this plot is for, if you have a measure at all, and you have 1, where do you put it? And this tells you. And then the first point goes in whatever that is the best location. And after you put the other 3, so you have 4, that region that you were not going to learn anything important if it was your first one, now becomes like the next fine-tuning that you need to make.
Okay.
Yeah, that's certainly.
So in that sense,
Yeah, one could certainly deconstruct this. I just don't know the
I
answer.
was just wondering.
No, it's a great question. Other? Okay, so just to note to finish up here, we have these case studies, so it's important to have the examples of how this works if you want to extend it. We've heard a number of those. There's some other ones here that we haven't talked about. I'll go step through these a little bit before. There's some extra slides here if you want to know about any of those things that connect to what you want. We've heard about nuclear masses, I guess, here. There's some bonus slides here that I won't go through. There is the GitHub repo, version 0.2. The tools, again, were listed before by Ozga, and again, you've learned about 3 of these ones here, coming soon for version 3. What is the plan for that? Let me emphasize again here, by the way, so within the repo, if you use any of these, try any of these things, it's GitHub, so you can put in issues that ask for new features, complain about bugs, gently point out that there's bugs, and so on. So then finally, the timeline we started in July 2020. We started with COVID with a virtual Bandcamp, then a hybrid one. We're very happy to have you all here in-person Bandcamp. Version 02 came out last summer, so this summer the plan is 03 with all of these things. Okay? And we have at least a couple more summers leading up to the full functionality. And that's it. I want to mention there's a uncertainty quantification and emulator development summer school coming up in next month. And this is just a plug for something of mine. This is a course I teach at Ohio State, so there's a Jupyter book that has many things there, including things that we've talked about, like singular value decomposition and Gaussian processes, all with software. Okay. All right, so again, thank you all for your participation today, being great in working through these things, and let's go to the reception.